Yeah, perfect. Yeah, please go on.
Okay, excellent. Yeah. So, yeah, I'm sorry for the delay here. Partially due to the time zone, and partially my new computer is not fully set up yet. So, happy to be here talking, and actually did enjoy this presentation despite not understanding anything that was said, but the slides looked really good. So I wanted to start off just to say a couple of things here. So this workshop is really relevant for us at North Carolina State University because joint sensing and communication is one of the key aspects of what we call a smarter infrastructure. And it's one of the themes that we're exploring in 6G as part of this new center, 6G NC. And so the joint sensing and communications, and then the associated applications in vehicular and aerial, as well as the implications on new technologies when you can do sensing and communication with large apertures over many frequencies. We have a test bed at NC State, which is called AirPaw, which is a UAV 5G test bed. And so we have the ability to, at least when the test bed is done in about a year, test out a lot of these different ideas in the real world as well. So I was excited to move to North Carolina State University because of the expertise in a lot of different areas, in particular antennas and circuits, as well as in networking. And I think that antennas and circuits, signal processing AI, and networking all together are going to lead us to the innovations that are going to create something that we need to call 6G. And joint communication radar, joint communication sensing is an interesting area as it touches all of these different expertise. To really do something in the area, you have to understand and work with people with these different backgrounds, not to mention the folks in both sensing and communications in general. So in the talk here, I have a number of slides. I'm going to focus on, talk a little bit about just the infrastructure, and then a couple things that we've been looking at the last couple of years in terms of joint sensing and communication. So first on the evolution here, so I can see that the whole 2 days is full of talks on joint sensing and communication. So I don't think we need to go through all of these different slides, but I'll at least give you my perspective that, you know, we started looking at this with the idea of leveraging the communication capabilities already on vehicles for dual purpose to also do sensing. And so our original motivation for this was with DSRC, wireless communication, and saying that, hey, if we have the communication capability, can we use the echoes for radar as well? And then over time, we started looking at other topics related to a millimeter wave, and that got us interested in the radar problem. And then we saw many other applications of sensing and communication different that they could be put together. And in the near term, you know, in the vehicular applications, I mean, the vehicles are getting the sensors, but in the long term, we see that it's the base station where the intelligence is going to, not just the intelligence of the computing, but also the sensing, more and more is going to be pushed there. And so one of the main questions is, you know, what can you do when you have sensors available at the base station, aside from doing automated driving, positioning, localization, the things that they're designed for. And this is just a little bit about, you know, the different sensors, cameras, radar, LiDAR. The main points is that these different sensors are operating in different frequency bands. So camera is passive in the optical band. There is some active cameras, like especially infrared, but for the most part, it's passive. Radar is operating at millimeter wave. Right now, 90 gigahertz, but shortly, and it's going to be above 100. There's a lot of interest there. And then LiDAR is an active sensing also in the optical region. So you've got different electromagnetic signals being used for sensing as used for communication. That said, they're all operating in the same environment. And that's the key idea that we want to exploit. So my colleague that you saw, one of her papers referenced earlier, Professor Gonzalez-Brelchich, has been pioneering this idea of using the sensors to aid communications. And the key idea is that you may have communication and radar that are operating in different bands, but the bands are proximate. And so there's something learned at 77 gigahertz that can be useful at 70 or 60 or 38 or 20. And what she's done that I really like has been not just formulating the problem, testing it out in ray tracing, but has also done experimental work to try to validate these different conjectures. And that work shows that it is possible to learn something from the radar to aid the communication. And Dr. Zhu in the previous talk highlighted some of the applications of this, for example, detecting a blockage, in implementing a new beam training strategy based on what's detected by the sensor. And so one of the things that I think that people are not fully realizing yet is that the sensing at the base station has a lot of value to different people. So in the US, it's very difficult for companies to get access to city infrastructure for communications purposes. I mean, they can get access, but there's a lot of paperwork and time and permits required. So and the city doesn't get anything really from the communication, but if sensors are deployed on the infrastructure, the city could get data that it can use to run better. For example, transportation, it can know the flow rate of vehicles, bicycles, pedestrians on all different kinds of streets, and it can use that to adjust the lights and to make other infrastructure adjustments to improve throughput, reduce latency, and make the environment safer and more efficient. So the sensing, this ICS idea, it gives the cities data that can be extremely valuable. It also helps to, gives a different perspective than the sensors on the vehicles. So that's a big plus. And then finally, it also helps in terms of even non-connected users, vulnerable road users, pedestrians, bicycles, scooters who may not be connected, nor may have automation capability, can still be served with that infrastructure. And so sensing is going to make infrastructure an even bigger part of our lives than compared with cellular. And I think whereas cellular, the infrastructure was hidden away, with sensing, it's going to be coming back probably to where we can see it, because we want those sensors to be able to see the environment as well. Now, this idea of using sensors to aid communication is quite interesting, but it's a lot of challenges associated with it. Some of the challenges are really, so intuitively we understand there's a connection between the propagation environment and the communication channel, but we don't have good mathematical models for this. So this is an opportunity for machine learning. It's also a little bit difficult to imagine how to connect the communication into the communication stack. And this is an example from LTE, and this is an automated vehicle planning stack that shows some of the different layers of fusion that happens with the sensors for trajectory planning, motion control. And so there's sensors that are operating with different timescales, different information. And so there's an opportunity to develop these interfaces for sensing to go into communication. And it's certainly not there now. And I think it's going to be an idea that needs a lot of effort and changes in the standard to make it work. Even if 5G evolves to have AI ML, this is that plus much, much more. So this brings us to ML here. Nuria and I have a series of nice cartoons on machine learning, making fun of machine learning for everything, although it seems that ML for X, instead of being a joke, is actually now a mainstream term, which is even more funny for us. So some of the places that I think that machine learning is really important in this application, basically to uncover those correlations. And so this is one that Dr. Zhu highlighted, recommending a subset of beams based on site information. So we know that Sometimes this link is blocked, sometimes it's not, so that information can be used to reduce beam training time. You could also use, that's position-based, but you could also use the raw LiDAR point cloud to train something that's even more sophisticated. And LiDAR is getting a higher resolution view of the environment, but still it's limited based on its position. And we've done some work with LiDAR as well. And this is just examples of some other things that we've done. And of course, this has become a big topic in the community now, looking at the different kinds of sensors as a form of site information for communications. Now, while most of the applications I was highlighting here, like radar and LiDAR, are active sensors, where the sensor is generating a signal and listening to its echo. In other envisioned applications of ICS, you could imagine that there's a passive array that is located at the base station, but it's not generating a signal, it's just listening. And so one of the papers I highlighted earlier, Professor Gonzalez's work on overhearing automotive radars, so that the cars have automotive radars which are sending, and you can overhear those signals and estimate the channel between the radar and the base station. Of course, you have to make some assumptions about the parameters of the radar, and there's a lot of interesting challenges there, but it becomes another source of information that can be had essentially for free, because you're not using spectrum for communication and you're just passively sensing. So there's not even a huge power consumption penalty there. So the sensing can also be passive. And I think one of the challenges here, also highlighted in the previous talk, is that when you start going from a pure communication environment to sensing plus communication, you need the ability to co-simulate both sensing and communication simultaneously. And what we've done is been primarily, we have focused on using ray tracing tools, and with colleagues, Professor Clautel in Brazil, Professor Gonzalez Prochich, and some former students, we developed a really nice simulator that uses a traffic simulator to place cars and buses. It uses ray tracing to predict the channels. It uses Blenser to do cameras and LiDAR. We can also do radar simulation using the same ray tracing outputs. And there's a lot of work. And so this is an area that I think it makes communication simulation challenging, because we've done a lot of, look at all the models in 5G, the things that are in Quadriga. I mean, they're all based on simulation, inspired by reality, but now we really need a much tighter coupling between reality and the channel model and all the application, because the ways that, for example, object detection works is going to be different if the environment is crowded or not, and that affects how the radar looks, and it affects the communication channel. All of these things are packaged together. That's one of the big challenges. So in the last few minutes, I'm just going to highlight a couple things here. First, I'm going to mention just a little bit of the more recent work that we did combining communication and radar, and then I'll wrap up with a couple of the experimental results. Our initial motivation for combining communication and radar, as I mentioned, was really just a matter of hardware reuse. And so we were looking at the case where the cars are already communicating, we use the echo for radar. And so in our initial work, we established this idea of using 802.11ad to do ranging. And then in subsequent work the last 2 years with my former PhD student, Preeti Kumari, we looked at generalizations of that work to get better Doppler estimation by modifying the waveform, to get better spatial resolution by optimizing the beamforming, and then finally we did some experimental activities. And I'll highlight just briefly the waveform idea and then the experimental activities idea. So on the waveform idea, our initial work, so all of our work was based initially on 11ad, because we started this in 2015, I think actually late 2014. So this is well before 5G was finalized. And so we were trying to build this joint communication radar platform on an existing millimeter wave standard. And 11ad made a lot of sense for us for a vehicular system. And the way 11ad works is packet-based, so there's a preamble, and then there's a packet. And so we were just using the preamble to do the radar ranging. And the preamble of 11AD has a whole bunch of Golay sequences. They have good correspondence properties, and they're really good for ranging. The problem is we don't get enough, the preamble is very short, so we don't have enough looks at the channel to do good Doppler. And so this is just highlights of other work. I'll show the slides here. And so to get better velocity estimation, but we wanted to make minimal changes to the standard. So how could we do that? So essentially what we did is decided to leverage some of this work that's happening in sparse sampling, where you sample with irregular intervals. And the idea is like, you imagine sending a packet that has different lengths. So it still has the same header, it still has data, but the preambles occur within a particular, specially designed interval, so that when you look at several preambles together, you can estimate with very high accuracy Doppler and range information. And so this is the idea. We wrote a nice paper on this that just appeared late last year that explained the concept. And it turns out by having this irregular spacing, you can do a lot better than with a regular spacing. And then finally, I just wrap up to say that, we've been working on this for a while. We started at lower frequencies. It might even have been 2013, I forget now. We had a project where we were implementing an 11P based radar system with Toyota years ago. But we really wanted to test the concepts out. And so we looked at different options, 11AD Wi-Fi. We kind of figure out how to get the output data so we could do the ranging. There's a lot of work on cellular prototypes, and relatively speaking, you have a lot more control over such prototypes. And so we decided to leverage that solution as well. And so what we did is we ended up prototyping a SIMO joint communication and radar setup, where there's a source that's transmitting to a destination, and at that source, there's also a receiver that's listening to both the crosstalk as well as the reflected signal, and then applying radar on top of that. And then just to make the problem more interesting from a research point of view, we also looked at what happens as a function of resolution if we have a large ADC, a large array, but we reduce the resolution of the ADCs. So I'll skip some of the details here, but basically, what we did is we compared our results with an automotive radar, a software-defined radar. And so we co-located the radar, and in this case, this was the receiver, and we used reciprocity to emulate a SIMO system by varying the locations of the transmitter. So we couldn't do anything with Doppler with this, but we were able to create this virtualized MIMO channel, and we were able to compare the conventional automotive radar processing with our processing, as well as the data rate obtained on the communication link. And we used corner reflectors so that we could get realistic point sources. And so we implemented a couple of very advanced algorithms in several different environments, and we found that our system had better range and azimuth capability. This is really because we had more virtual antennas than the automotive radar, and we also had more bandwidth. So it's not too much of a surprise. But the other thing that was interesting was that we were able to get very good performance when we applied some smarter signal processing algorithms on top that aren't normally used, and expectation maximization GAMP. We also found that we could get really good performance even with just 2 bits of resolution at the receiver. So 1 bit not quite enough, but 2 bits is okay. So this means that there's opportunity to make this work with very low power. We had done this with different experiments with 2 corner reflectors, with a bicycle, with this was radar communication comparison, and then we had, maybe this one was the one with the car, I can't remember now. But we looked at a lot of different scenarios, and essentially we found that this idea of communicating a radar together is viable. I mean, it needs work. you know, because the range of a communication link versus a radar link is totally different because the radar signal has to go and come back. So it has a lot more loss. But there's enough evidence between this work as well as other work in the community that joint radar and communication is possible. And it's something that I think that we should really design 6G around. And so that's it. I'll stop here. I'm really sorry again for being late. The plus is I'm talking in the evening, so I can drink wine while I'm presenting.
Okay, thank you very much, Robert. Thank you for joining us and for sharing your recent research outcome. Actually, as we are running out of time, so I'm sorry that we may not have time for questions, but if any, we may do it online. So there's online broadcast and you can send your questions, so maybe you can respond online. So I will stop here. Thank you again.
Yeah.
Thank you.
Yeah, thank you.
Okay. All right. Thank you. 这个很抱歉，这时间比较紧，我估计我不能给大家。